Okay, we're going to look at a simple algorithm for calculating the quantity of ingredients for making pizzas. So my pizza dough recipe has 229 grams of flour, 100 grams of water, 1 gram of yeast, and then 6 grams of salt. So, how much of these ingredients do I need to make 3 pizzas? Simple, right? Take 229 times 3 for flour, 100 times 3 for water, 1 times 3 for yeast, and 6 times 3 for salt. So I need 687 grams of flour, 300 grams of water, 3 grams of yeast, and 18 grams of salt. Simple calculations. How can I write a C++ program to do these calculations for me? So we've seen how we can do numeric calculations to figure out how much of each ingredient I need to make my pizza. You're certainly capable of doing the mathematics for that. I could give you any number of pizzas, 2 or 1,000 or 6, and you could calculate the amount of ingredients we need. One of the things that we do in computer science is we make computational processes very explicit, and we formally state these computational processes, and we call those algorithms. And then we take the algorithm and we implement it using a programming language. And this distinction is incredibly important, and it really is what separates computer scientists from programmers. So first of all, what is an algorithm? Informally, it's a well-defined computational procedure. Let's not worry about what well-defined means at this point. This is what you will learn over the course of your study. And it takes some value as input, or it could be a set of values, and it produces some value or set of values. And this is what we call output. So that means that an algorithm is just a sequence of computational steps that transform the input into the output. And this is from a very authoritative book. We use it in our curriculum. Most universities use it in their curriculum. If you look around, informally it's known as CLRS. An abstraction of these words is that we have input, it goes through some processing, and then we get output. Abstractions are also very important in computer science. This is a very simple abstraction of an algorithm. In reality, algorithms are much more complicated. They don't just take input, do processing, and give output. There could be multiple input at various points of processing. We can also represent an algorithm as this sequence of steps. Here we're doing it graphically. Generally, this is known as a flow chart or a flow diagram. And then we also write algorithms in this step-by-step format. So for making our pizzas, what is the input? Well, we have to know the number of pizzas. And then what is the processing? Well, we have to figure out from the number of pizzas how much flour we need, how much water we need, how much yeast we need, and how much salt we need. And once we've determined those quantities, that's our output. What's an algorithm for calculating the ingredients we need for some number of pizzas? Well, the first thing we need to do is we need input. So we have to figure out how many pizzas we need to make. Then we need to calculate the amount of flour needed, calculate the amount of water, yeast, and salt. Once we've calculated these quantities, then we can output the amounts of flour, water, yeast, and salt. Now, this is an algorithm that I have presented as a sequence of steps. I am also using a lot of English to express the algorithm. Algorithms can be informal or they can be formal. They can be very mathematical in nature. We also adopt certain languages for expressing algorithms, just like we have different languages for expressing computer programs. So one thing I might do is I might shorten things and say input pizzas. And now pizzas becomes a symbol that represents the number of pizzas that I am going to make. And now I can calculate the amount of flour, which is 229 grams, times the number of pizzas I want to make. And you can see that I'm using some informal mathematical notation here to express my algorithm. And once I have calculated the 4 quantities, then I can output those quantities: flour, yeast, salt, and water. I can be even more formal in the statement of my algorithm. And again, we can use a combination of math, programming language constructs, and English to express an algorithm. So here, notice that I am bold-facing input. And instead of using pizza, I'm using a variable with a single letter named P. P might be difficult to understand if you didn't know what I was talking about. So sometimes it's good to be explicit, but I'm illustrating here how algorithms can be a little bit more formal and a little bit more abstract. And now I can represent my calculation using F, left arrow. Left arrow is called gets. We often use the left arrow to represent assignment. The equal sign sometimes has meaning other than assignment. Maybe it means equality. And so we have to have symbols that are unambiguous when they might represent different types of operation. And then I'm using 229 and dot P. And again, dot is a common symbol that we use for multiplication. I can finish out my assignment statements and calculations using the same notation. And finally, I can just output the quantities that I've calculated. So I've shown you 3 different ways of writing an algorithm if we're talking about steps, but we also have graphical ways of depicting an algorithm. I've already mentioned flowchart and flow diagram. We start with a symbol, right? This tells us where the algorithm starts its execution. And then the reason they're called flow diagrams is because we have these arrows that you follow and you flow to the next step of the algorithm. The parallelogram in flowchart language stands for input and output. And so here we are inputting the number of pizzas. Then we flow to the next steps of the algorithm. Rectangles in a flowchart language represents a calculation or a process of some sort. And here I'm calculating my 4 quantities. And once I finish with my 4 quantities, then I can output them, and then I flow to the end of the algorithm. So now we come to implementation. Once we have an algorithm, then we can implement it as a computer program. Well, why don't I just start with the computer program in the first place? Well, an algorithm lets us express the essence of the computation that we need to perform. It lets us express the essence or the most important parts of the computational process. And you'll see when we get to writing programs, there are a lot of details that we have to worry about. And we don't often have to worry about those things when we're talking about an algorithm. For example, here in my flow diagram, we know that all of these quantities are represented in grams. And we can kind of abstract away the fact that we're talking about grams. But when we're talking about a computer program, it might be very important to tell the person running the program that you're expressing quantities in terms of grams instead of ounces. And you'll see that in the computer program when we get to it. So, very important, we have an algorithm, step-by-step process for converting input into output, and then we implement an algorithm as a computer program. Now that we understand the process for calculating the amount of ingredients I need given the number of pizzas that I want to make, let's turn that into a C++ program. You may not know all the C++ that I'm going to use in this tutorial. That's fine. That's what your class is supposed to teach you. Maybe a few weeks into your class, come back and take a look at this program. But I'm going to take you through a series of steps and gradually develop the program by building it up and using more and more complicated constructs. This is a process known as incremental development, and it's very important. You don't write computer programs like you write history papers. You build a program up gradually over time. I'm going to use VI because I'm just much more efficient using VI. The program that you see on the screen is a very good starting point for most programs that you're going to write in C++. And you can gradually build it up into more complicated programs. The first line of the program, this pound include IOStream. This includes a library called IOStream, or input-output stream, that contains functions and objects that let me write information to the console or read information from the console keyboard. There are a lot of other libraries that we can include. This is the only one that we need. The next statement, using namespace std or using namespace standard, just tells the compiler that everything in the program that I'll be using is declared in the standard namespace. For simple programs, this is fine. There are other ways of handling this issue. You probably won't need to use namespaces until you get into industry. They are ways of avoiding name conflicts in large computer programs. This is the main function. That is the entry point for all C and C++ programs. That's where, given a very large application, this is where execution of the program starts. Int means integer. This is showing that the main function returns an integer. And here I am returning the integer 0. Returning the integer 0 indicates that the program terminated correctly. The caller or the operating system can use the return type of the main function to know that the program terminated correctly. So now I can start writing my C++ program. And I'm going to focus on flour before moving on to water, yeast, and salt. Let's say that I want to make 3 pizzas, and we know that I use 229 grams of flour. So I can say 229 times 3. We're using the asterisk as the multiplication character. Now this is a program that will compile and run. To compile it, I say g++ pizza.cc, and it tells me that I have a warning. Now it's doing the calculation, but I'm getting a warning because the result of that calculation is not being used by the program. What I want to do is I want to print out this quantity to the console. I can do that using cout. Cout is an output stream that is associated with the console. Then to print this quantity, I use 2 angle brackets. These 2 angle brackets form an operator called the stream insertion operator. It inserts whatever is to the right of it. So in this case, it will insert the result of multiplying 229 times 3. Now I can compile and run this, and you see that I get 687 and then the command prompt. It's messy output. Also defined in IOStream is a stream modifier called endl, and this will give me the new line character after input finishes. So now if I compile this and run it, you can see that it prints 687. Now we know that 687 is the amount of flour, but someone else running this program might not know. So it would be helpful if we put a little prompt here that tells me what this quantity is. Compile and run this. Now it tells me that I need 687 grams of flour. What if I want to make 2 pizzas or 5 pizzas? I have to edit my program. The other thing that I would like to avoid is using these hard-coded numbers, especially since you might use hard-coded numbers multiple times. It's often convenient to define them once. So I know that I'm going to multiply the number of pizzas times flour, water, salt, and yeast. So I'm going to declare a variable called pizzas, and I'm going to store in it the number of pizzas that I want to make. And now I can use that variable by storing it there. Compile and run. And I'm calculating 687 grams of flour. Ultimately, we don't want to have to recompile the program anytime I want to make a different number of pizzas. So I want to get this quantity from the keyboard. So I can assign pizzas to the quantity 0 as its initial value. And now I can get the number of pizzas from the keyboard. CN is an input stream that's associated with the keyboard of the console. These two right angle brackets form an operator called the stream extraction operator. It extracts a quantity from the input stream and it stores it in the variable to the right, which is pizzas. So now I can compile and run this. And it is sitting here waiting for me to type something. Now, some other user might not understand that it's waiting for input. We'll fix that in just a minute. Someone might think that the program is hung for some reason. But if I type in 3 and hit enter, then it calculates the amount of flour I need. If I type in 2, it calculates a different quantity. What would be helpful is a prompt, so I can use a cout statement. So now the user knows exactly what's happening. I get this prompt, how many pizzas do you want to make? And now they can type in 4 and it calculates the quantity of flour that I need. Most people are going to know when they see certain amount of flour that that's the ingredients you'll need for the pizza. But let's just make it really clear. And then I'm going to put a little indentation here just to make things visually. Type in 3, it tells me you're going to need the following ingredients, and I need 687 grams of flour to make 3 pizzas. I also want to take the quantity of flour and store it as a variable. And we do this a lot when we're writing programs. We often prefer a variable instead of some numeric quantity. It makes your program more symbolic. And if you were to use a quantity like pizzas multiple times, it's a lot easier to change if you have a single number to change that's stored in a variable, but that variable is used multiple times. It's a little hard to make that point in this simple program, but you'll see how I'm using pizzas in just a minute. And so now I can change this to flour. There's my output. So now this is a pretty nice program in terms of its structure. One final little point is notice that the value of pizza changes. Pizzas starts off at 0 and then it changes to whatever quantity the person enters on the keyboard. However, the value for flour will never change unless, of course, I change my recipe. So I am going to declare this as being a constant using the const keyword, and this ensures that the program can never change flour or the quantity stored in flour. Compile and run. Okay. So now I can finish it out. Now notice how I have focused on getting the program to work with just flour. And now that I kind of have an overall structure that I like, I can expand it and deal with yeast and salt and water. This is known as incremental development, where you gradually build up a program over time. It's a very important skill to learn. It manages the complexity of software development. So now let's add water, yeast, salt. If you remember, I use 100 grams of water. I use 1 gram of yeast and 6 grams of salt. I'm going to compile just to make sure I didn't make any mistakes. It's good, after you type in a bunch of code, and what a bunch of code is depends on how experienced you are. It's always good to give it a quick compile to make sure that you haven't made any mistakes. Doing that somewhat frequently helps you manage any compiler errors. Now I need to finish my output statements, and what I'm going to do here, instead of typing, I'm going to use search and replace. In VI, the dot means the current line, S means substitute, and I want to substitute flour for water. And then the G makes sure that I change all instances of flour to water on the entire line. So you can see that it changed flour in both places. So I'm going to do the same thing here, except I'm going to change it to yeast. And I'm going to change this flour to salt. Now I'm going to compile, and let's give it a run. I'm going to make 2 pizzas, and I'll need 458 grams of flour, 200 grams of water, 2 grams of yeast, 12 grams of salt. So that's a simple C++ program that lets me calculate the amount of ingredients I need for, given the number of pizzas that I want to make.